All right, so welcome everybody to the second of our AGU Geodesy Section webinars. We're very fortunate today to have Surendra Adhikari as our speaker. Surendra is the co-recipient of the 2021 John Wahr Early Career Award for the Geodesy Section. So we're very honored that he has agreed to try us this new experimental webinar. So thank you all for joining us in this experiment. I think it will be very interesting. Just as a little brief introduction about Surendra, he received his PhD at the University of Calgary about 9 years ago. Following, before that, he'd gotten a Bachelor's of Engineering degree and a Master of Science degree. After graduating, he's been a postdoc at the California Institute of Technology, as well as the Jet Propulsion Lab, where he still remains as a research scientist. And so today, he's going to talk to us about ice-Earth interactions in Greenland across timescales. So please get started, Surendra.
Thank you, Matt. Can you hear me? Can you hear me okay? Or
yes, we can hear you.
Okay, cool. Thank you. Well, thank you so much for the opportunity. So thank you everyone for tuning in. Thanks for your time and interest. I really appreciate that. So I take a moment to thank the AGU Geodesy Section Committee for recognizing my small contribution to this wonderful field of geodesy. So it means a lot to me, and it's gonna only encourage me to do, more useful science in the future. So thank you so much for that once again. So in this talk, I'm gonna basically showcase some of my recent works on Greenland ice-Earth interactions. So I built this talk about the crustal motion data measured by GNSS stations, and I'm gonna interpret some of the GNSS signals in light of ice-ocean mass exchange across timescales and the induced deformation response of the underlying solid Earth. So my hope is that by the end of this talk, I really want to get across two key ideas that I think are very important to realize. The first one is that the future loading strategy in Greenland should consider more comprehensive rheological models than typical classical Maxwell models in order to capture mental relaxation processes that operate across a range of timescales. And the second message that I like to convey is that the GNSS-based measurement of ice-Earth interactions holds a significant potential towards continuous and near real-time monitoring of mass transport through outlets through Greenland outlet glaciers. So these are the key points I like to really get across in the end of my talk. But before I get into details, I like to take a moment to acknowledge contributions from my collaborators. So they are mostly from JPL, but they also represent University of Ottawa, Technical University of Denmark, Geological Survey of Denmark and Greenland. And I'm very thankful to NASA program managers, particularly those representing NASA Earth Surface and Interior Focus Area, NASA CRISPR program, and NASA Sea Level Change Science team. So as I said earlier, this talk revolves about the bedrock GNSS data. So it is really appropriate to show the present configuration of GNSS stations in Greenland. And this network of stations, GNSS stations, is formally called GNet, Greenland GNSS Network. So this initiative was led primarily by the Ohio State University, the Technical University of Denmark, UNAPCO, and University of Luxembourg. So some of these GNet stations have been in operations for more than 2 decades now. So they give us a precious set of data that we can look at, and we can interpret those data in light of ice-Earth interactions across timescales. So in this presentation, I'm really interested in interpreting some of this data in light of ice-ocean mass exchange, in general, climate-driven surface mass transport, and the induced deformation of the underlying solid Earth. The working principle is fairly straightforward. And so here's a really nice schematic that shows the working principle of that that my analysis actually is based on. So if we apply certain load on the crustal surface, so it's going to induce the deformation of Earth materials, and that can cause the surface displacement on the crustal surface. which can be potentially measured by deploying GNSS sensors. And so in our application, the surface load actually is primarily related to the change in glacier load. So glacier changes its mass all the time as it responds to ever-evolving climatological forcings, in particular atmospheric forcing and oceanic forcing. So here's a quick look at the three-dimensional displacement time series for one of the GNET stations. So you can see all three components, the up-down vertical component and north-south and east-west, the two horizontal components of the displacement vector. So these are the daily displacement data. And so, a lot of processing has already undergone to come up with these results. For example, we had to take into account the impact of ionosphere and atmosphere in terms of delaying the signal. And also we had to correct for the solid body tides and the ocean loading tidal effects, from the signals. So one of the outstanding feature that is common in all three components of displacement vector here is the underlying secular trend. So for the horizontal components, you could see that the Greenland is moving, especially this station is moving in the direction towards northwest, and which primarily represents the tectonic motion of Greenland, along with the North American plate. Whereas we are not interested in interpreting those signals, but we are rather interested in interpreting the secular trend associated with the vertical component of the displacement vector. And Greenland, by and large, is a cratonic region and having a minimal intraplate and seismic activities. So we can largely interpret the secular component of the vertical component of displacement vector in light of the climate-driven surface mass transport on the surface across time scales. So, and this would be one of the main topics of this presentation. When we remove the underlying trends and acceleration trends, from this data, then we end up having some exotic-looking signals. And some of these signals are really systematic. For example, you could see a seasonal cycle here, but at times these signals can also look chaotic. For example, in this horizontal component of displacement vector, we could see a sudden shift or jump in the bedrock position. So our goal here is to also try and interpret some of these signals, mostly in light of contemporary surface mass changes, because for the non-secular time scale, Earth's rheology can be excellently approximated by the elastic Earth model. Okay, so let's get started with the first part of this talk, which is really focused on the secular component of the vertical, secular trend in the vertical component of the displacement vector. So in short, I'm going to call it uplift rates simply. And so here, the goal is to try and analyze these uplift rates. And in the process, we'll see, what lessons we can learn about the mechanics of Earth's deformation. The circles here show the measured uplift rates, and the bigger the circles, the larger the uplift rates. The background map shows a CRISAT 2 based high resolution ice thinning map. And so you could see, pretty much one-to-one correspondence between the two data sets. So in the region where we have seen a significant amount of thinning, for example, in here, it's the same region where we have also seen the significant amount of bedrock uplift. So indeed, elastic Earth models predict significant amount of uplift rates, and which is compared here in this chart. So on the y-axis, I plot the model elastic uplift rates, and it is compared against the measured uplift rates, which is placed in the x-axis. So one-to-one line is shown with this one. So for certain stations around the southwest Greenland, so it looks like elastic Earth model is sufficient to fully explain the observed data. But that does not mean there are no other processes that contribute to the modern crustal motion data in these regions. So we'll talk about that in a bit. But in general, so just a few words about the elastic uplift rates calculation that we conducted. So we have been very careful in terms of computing the signals. And for that, we have propagated uncertainties not only from the surface, not only as the uncertainty associated with the surface load, but also the uncertainty associated with the Earth structure, elastic Earth structure. So as for the surface load model, we use the CRISAT 2 based data set, which is truly a kilometer scale, high resolution data set of ice thickness changes. and we had to use appropriate front air content correction, for which we relied upon the RACMO model predictions. And it is also important to capture the mass changes happening in the adjacent regions, in particular the Canadian Arctic, which is not located not too far from the northwestern part of the Greenland. So we also take into account the impact of the mass changes happening in the North Arctic on the Greenland coastal motion. And as for the Earth structure, so we primarily rely upon the standard one-dimensional Earth model, which is PREM, preliminary reference Earth model. But we know that the short time scale, the short wavelength signals of the displacement field is really impacted by the shallow part of the crust, and for which we try to capture the three-dimensional structure, the impact of the three-dimensional structure in the shallowest part of the crust, for which we use the crust 1.0 data set that is arguably much more better than the PREM data set, because it captures, it relies upon the much more denser teleseismic resampling, and it could resolve 3 layers of sediments and 3 underlying layers of crystalline crust. So, but the main upshot here is that the impact of the three-dimensional Earth structure is really minimal compared to the uncertainties associated with the surface load. But anyway, so as I write here, the elastic Earth models, predict significant amount of uplift rates, but not really sufficient to fully explain the observed data. So it means that we have to also look at the other plausible sources of the signal. And for that, so we should really look at the range of time scales over which mass is being exchanged between ice and ocean. And so if we may, we can really go back to the time scale of 100,000 years, which is really the time scale that associates with glacial and a glacial cycle. But really what is important here is the deglaciation sequence since the last glacial maximum that peaked sometimes between the past 20 and 30,000 years. And also it may be important to take into account the impact of the short time scale, relatively short time scale climatological phenomenon, for example, the ones associated with the little ices, and this kind of relatively short time scale, or relative to the time scale of last glacial maximum or the glacial and glacial cycle. And it may be important to also take into account the potential impact that the mass changes happening during and after the ices on the modern measurement, the GNSS measurement of crustal motion data. So just a reminder that the past ice ocean mass exchange has been fairly well constrained, and of course there are a lot of room to improve in pretty much every respect of this wonderful field of past ice, the paleo surface mass redistribution. But tremendous efforts have been put together to utilize the available remote sensing data, available relative sea level data, and also maybe ice exchange data and many other geological proxies to constrain ice ocean mass exchange across time scales. And here, what is really relevant is that for this ice ocean mass exchange across time scales should have some contribution to the GNSS data. And so in fact, the GNSS data should have measured the elastic response of the Earth to the contemporary surface mass changes, which is really constrained by the satellite remote sensing data and airborne altimetry and so forth. And but the signals should also comprise of the ongoing viscous response of the solid Earth to the past ice ocean mass exchange. And so in the previous slide, so we all we did was we looked at the role of the elastic Earth deformation to the observation. So now the viscous response is typically modeled or captured using the so-called glacial isostatic adjustment models. So there are quite a few models that are dedicated, well, not many actually, that are dedicated to Greenland. And so one of the most comprehensive efforts is the one by Glenn Milner and his colleagues at University of Ottawa and elsewhere. And their model, their effort really traces back to the work of Simpson in 2009, and maybe even further back. But a couple of papers by Cavalier and Simpson, what they really did was they used the paleo sea level data and the ice extent data of the past to constrain both the deglacial load model, which is based on the dynamical ice sheet model of Philip Huybrechts, and also they try to find the optimal one-dimensional Earth structure. And so what they found was that for Greenland, the thickness of lithosphere is about 120 kilometers, the optimal thickness, and also the optimal upper mantle viscosity is 510 to the 20 mass pascal second, and the lower mantle is much more stiffer than that. So this is really, these are the typical values that represent the cratonic regions. So Greenland is really, so cratonic in a sense that there is not much intraplate activities, or there is no evidence for the asthenosphere, the presence of the weak asthenosphere or so forth. And recently in their 2018 paper, Glenn and colleagues, they tried to also experiment with the impact of the three-dimensional Earth structure on the model GIS signals, and for which they relied upon the 2 lithosphere thickness model and 4 mantle viscosity models. They were primarily constrained by the seismic velocity data. And so, of course, there's a lot of uncertainties as to translating the seismic imaging in terms of the mantle viscosities, for example, but they did a handful of, they showed a handful of methods and just a limited, possible translation, from the seismic information to the information that could be used to constrain the mantle viscosity. And they used this limited number of possible 3D Earth model, not to compute the comprehensive impact of the 3D Earth model on GIS signal, but to get a sense of how much impact it could make on the three-dimensional on the GIS signals. And here's what they came up with, and this is the mean GIA uplift rate. They present the uplift rate due to the GIA processes, and this is the associated uncertainty here. So a couple of features that stand out here is that, so there is a large uplift ongoing on the northern part of Greenland, but in the southwest of Greenland, so there is actually the subsidence ongoing because of the GIA processes, and it has something to do with both the neoglacial advances and also the collapse of the foreballs associated with the former Laurentide ice sheet. So when we combine the elastic model solution and the GIA model solutions and compare against the observation, then we end up having significant data model misspeed, and which is really shown here. And so the misspeed is on the order of a couple of millimeters per year in the northern part of Greenland, but it is really significant in the southeast region and also the central west and the northwest. And it could be as high as 7-8 millimeters per year at certain locations. And here I must confess that there is inherent non-uniqueness associated with GIA models, and it is really rooted to the fact that there's a lot of uncertainties about both the Earth structure and the deglacial load model. But nevertheless, it is generally agreed that these residuals are robust and require additional geophysical explanation. So one of the leading hypotheses to explain this residual data model misfit is that the ongoing solid Earth response to the deglaciation of Greenland and peripheral glaciers since the little ices should explain the residual uplift, and which means that the highlighted, the mass transport phenomenon happening in this highlighted period is really something that should be, that should be contributing, that should be responsible to explain the data model misspeed. And the logic behind this hypothesis is fairly robust. And so the first thing is that the GIA models that we discussed a bit in one of the previous slides cannot really capture the high frequency, relatively high frequency, deglaciation sequence, such as, the post-little ices deglaciation in their model. And partly because these models operate on a really long time scale, large time scale, and they have the delta T in their model is typically on the order of 500 years or something. And the second thing is also to, second and probably the most important thing to realize is that, so Greenland actually has seen a significant amount of mass loss in the little ices. So it could be, more than 15,000 gigaton mass has been, transported from the ice sheet into the ocean over the past 150 years or so. And this is not a negligible amount of mass changes, and it must have. It's hard to believe. It's hard not to believe that this significant amount of mass transport would not have some contribution to the present-day GNSS data. So here's a quick look at the high spatiotemporal resolution of the Greenland mass balance reconstructions over the past 150 years or so. So you can see the little ices reconstruction of mass, which is really is the mass anomaly relative to the present-day Greenland ice sheet mass. And it also includes the peripheral glaciers, by the way. And so here you could see the time series of mass changes. So specifically, there was a large, relatively large rate of mass loss that happened in the period between 1920s through 1960s. And so it has, primarily, it primarily comes from the contributions from the peripheral glaciers rather than from the ice sheet. But anyway, so now the question is, if we include this, reasonably well-resolved deglaciation sequence in little ices, if we include this in a typical GIA model, it's not going to really solve the problem, because the level of improvements that it could give is at the level of sub-millimeter per year, which is shown really here. So here what we see is for a typical GIA Earth model, we force this model by this deglaciation sequence, and for a number of lithosphere thickness, so no matter what thickness we choose, we're not going to get the significant amount of uplift rates that is required to fully expand the residual, which is on the order of 3 to 5 millimeters per year. And we also conducted some experiments to answer a question like whether it is the three-dimensional Earth structure that can whether it can mask some of the residual. And answer is generally no. And here again, I plot the residual signal that requires further explanation. And on the upper panel, I saw a couple of representative three-dimensional Earth model predictions, in response to the post-little ices deglaciation sequence, which I introduced in my previous slide. And in general, pretty much everywhere, the impact of three-dimensional Earth structure is again at the sub-millimeter per year level. But except for, in the region, in this center east Greenland, so three-dimensional effect can capture or may explain up to 50% of the signal. And this is where we have the largest misfit anyway. But the fact is that, this is also the same area that is being affected by the Icelandic hot plume. And so here you could see at 180 kilometer depth, the mantle is really weak in this region. And it is really important to realize that this effect is really localized, and it does not really represent what happens in the rest of the Greenland. So that's why, we decided to exclude a couple of stations that have been most heavily affected by the Icelandic hot plume effect from further analysis. And we followed that, previous studies such as the one paper by Avaskana and others in 2016, they also decided, they also treated, those couple of stations kind of with a more kind of spatial emphasis on giving more, attention to the Icelandic hot plume effect. Okay, so now we are having a reasonably well-defined inverse problem. And so we are now looking to find a proper combination of parameters that could best explain the data model speed. And for which we chose to use a simple two-layer half-space Maxwell model. And the reason is that because we had to run thousands of model simulation, and we wanted to make it more efficient computationally. And so we did this parameter space exploration within a formal Bayesian framework. And we tried to vary two key parameters as we consider those as free parameters, the lithosphere thickness and mantle viscosity. And so we also try to, we also let some load-related parameters to vary freely. And so here is a rather simplistic representation of the little ice age or post-little ice age load model. So here you could see time in 80. So we are here, the present day. So this is the 1080. And we assume this to be the median year for representing medieval warm period. So we could see the mass anomaly, again, relative to present day mass. And so this is pretty much the little ice age. So after little ice age, we have much more, we have better constraint about the load history, of course. But during the little ice age, there is a limited, information that allows us to do, any better than what we have in here. So basically, we assume the ice sheet does not really evolve in terms of its mass over or during the little ices, and there's a gradual buildup of little ices emerging from the medieval warm period. So we let and we also let the duration of little ices to vary freely. So parameter 1 here essentially represents the timing of the inception of little ices, and parameter 2 represents the termination time of the little ices. And parameter 3 is related to the mass anomaly of the ice sheet during the medieval warm period. And parameter 4 is the mass anomaly related to the little ice age. And so we have some prior information to constrain the termination LIA time and the mass anomaly. And for rest of the parameters, we assume the uniform priors. So here is our results. You can see the probability distribution function, for all possible combination of parameters. So the yellow dots represents the model that has more likelihood to explain the data model, to minimize the data model misfit. And so there's a lot of information to grab out of this graph. For example, some of the most uncertain parameters, such as the little ice age inception time or the medieval warm period. So, our model solutions are really insensitive to those parameters because the yellow dots, so they spread across the plausible or the prescribed range of parameters. So which is a good thing. So, but the most outstanding feature that we have here is the strong correlation between the mantle viscosity and little ice age mass anomaly, which is shown in here. And so, which is not surprising, the model model featuring the larger LIA mass anomaly also requires or also favors the higher values for mantle viscosity. But the nice thing is that we know quite a bit about the little ice age mass anomaly. So we have a very well defined prior, and with the help of that, so we can really pin down the associated effective mantle viscosity, and we find that it is on the order of 6 through 11, 10 to the 19 pascal second. So, but the fact is that the mantle is not a half space, so it is really stratified, and the classical mantle, the classical picture of mantle is that it has upper mantle and lower mantle. And so if we fix the lower mantle value to the value used in GIA model, which is really constrained by paleo relative sea level data and ice section data, then we can come up with even smaller value of upper mantle viscosity, and which is on the order of 310 to the 19 pascal second. And it is important to realize here that the recent advances in seismic imaging show that there is no further need to stratify the upper mantle. So you cannot really invoke the presence of asthenosphere all over Greenland. And of course, there is the asthenosphere, if you may call it that way, in the region of in the southeast region, but it does not. It only represents the regional or the local certain part of Greenland, not the entire Greenland subcontinent. Okay, so now let's put the pieces of the puzzle together. So we have the GIA model that is really constrained by the geological data, and that has the upper mantle viscosity of 510 to the 20 pascal second. And what we have shown in this study is that if we need to also explain the geodetic data, the modern crustal motion data, basically, then we need to have a mantle viscosity, which is roughly 1 order of magnitude smaller than the typically used value in GIS studies. So this means that the classical Maxwell model is not going to solve us in terms of reconciling both the geological and geodetic data. And so one way forward would be to use the so-called extended Burgers model that can really capture the mantle relaxation across timescales. So here is a timescale. So this EBM model, by the way, is also supported by laboratory experiment of rock creep in a high temperature pressure environment. And also seismologists have recently made significant progress in terms of using or constraining EBM model to satisfactorily explain the post-seismic deformation. So here is a simple prototype for parameter EBM model. And the idea is just to demonstrate, the fact that it can reconcile, both seemingly time-dependent mental viscosity within a single modeling framework. So you could see as the, Maxwell timescale approaches, then the EBM model approaches or asymptotically approaches towards the secondary creep or the steady state creep, you may, which is really what is being captured by the Maxwell model, and the value is about 510 to the 20 Pascal, but in a relatively short time scale. And so this is about 10 years, or the time scale of GNSS observation, then we can really capture the low mental viscosity values using this model. And this model and this effort will have a tremendous ramification for interpretation of GRACE and GRACE column data, because now we have almost 2 decades of GRACE data, and the inelasticity of associated for this time scale is slightly larger than the one that is associated with the GPS data that we analyze here. So it would be important to further explore, to continue developing EBM model and applying it for loading studies in the future. So with this, I like to summarize the first part of my talk, so which is really shown here, basically, graphically. So the classical way of modeling crustal motion in Greenland is by combining elastic and GIA model. And if we just do that, then we are really underestimating the observation. So 1-to-1 line is here again. But when we apply the when we account for post-LIA deglaciation load model, then we can explain the residual, very well, but provided that the upper mental viscosity is 1 order of magnitude smaller than the typical values used in GIA model, which is constrained by geological data. So now this means that, so one way to reconcile the seemingly time-dependent mental viscosity is to use a much more comprehensive geological model than Maxwell model. And one example could be the extended Burgos model. And so it may be that, the future studies for Greenland loading studies, future modeling effort for Greenland loading studies should account for this EBM or, other comprehensive model if we want to unify load-induced deformation processes that operate across time scale. And so all of the data and models and Earth model and log numbers and data are actually hosted in this website, Vessel Virtual Earth System Laboratory, upsaplnasa.gov. I'll take a quick look at it, just to encourage you to check out this link. And so what you can see is you can choose any GNSS station, a GNet station, and then you can see, our best estimate of elastic model solution and the GIA model solution and this post-lethal ice induced deformation. And so this is the classical model solution, which is the sum of the ELA and elastic and GIA model solution. And this is our new estimate of the model uplift rate, and this is the observation. So you can literally walk through the station, and it's really interesting to see. And also what you can do is you can select any field that you want to highlight. For example, if you want to show GIA solution, and it just displays for you, and you can also play with the the C-axis limit, and you can click the download button for your own application. So yeah, please feel free to check it out when you have time. Okay, so I'm gonna now move on to the second part of my talk. So I should be done in about 15 minutes, hopefully. So now we're gonna switch gear a bit towards glaciology. So here we're gonna interpret the seasonal crustal motion, or basically non-secular component of the GNSS data. And our hope is that, because for this time scale, Earth geology can be approximated by the elastic Earth model, so it can interpret some of these non-secular signals in terms of, we can use these signals to constrain glacial mass transport. So here you could see the characteristic seasonal amplitude for the vertical component and horizontal components for a number of GNet stations shown with different markers. So basically what we can see that looks like over time, the seasonal amplitude has increased. at least for the horizontal, and also maybe to some extent for vertical. But the most outstanding feature here is that for year 2012, the seasonal amplitude is really large compared to the other years. And so this is really interesting. And so we'd like to see what is going on in year 2012 in particular, and specifically for a particular station data, which is the ring station data. And we want to understand and see what is really going on there, and hope to learn something about the glacial mass transport. So just a quick reminder about the climatological context of these signals is that 2012 has by far been the most extensive melt year that Greenland has ever seen. And here in the y-axis, you could see the melt area, the surface melt area of Greenland ice sheet as a function of summer days. And you could see in this color, so this is year 2012. And on a certain day of July 2012, the ice sheet was virtually was covered by the meltwater pretty much everywhere. And if you really think about this, it's a massive event, and it is kind of scary too if we really think about it. The whole ice sheet that holds the potential of raising sea level of about 7 meters was melting pretty much everywhere on a particular day in 2012. And so in fact, if we go back to the data, so we can see, the melting was so intense that, so it has its geodetic imprint in zenith data. And this is really what is reflected in here. And it just so happened that for a particular station called Rink, we saw really exciting, really interesting, intriguing feature, especially in the horizontal components. So here you could see all 3 components of a time series. I removed the underlying trends and acceleration from, and I did a bit of smoothing here, but the whole point was to produce this map, which is really different way of looking at east and north component of the displacement vector. So all you can see here is the plan view of the bedrock motion. The red line shows the trajectory of the bedrock motion on the horizontal plane, of course, during 2012. So you could see the clockwise motion of the bedrock. It's a significant, departure from where it started, and then made a big giant loop, and it tried to come back to where it started. And a similar systematic motion was also detected in year 2010, which is shown with blue line. And for the rest of the year, we did not see any systematic such motion. So during 2012, over the 4 months in summer, starting June through the end of September, I think, the bedrock was moving by about 7 to 8, maybe 9 millimeter in the direction of northeast. And then it tried to come back in the following 4 months. So now our goal here is to try and model these signals. And again, so there is no point to look at the Earth model, because the time scale is sufficiently. I mean, for this time scale, we can use elastic Earth model. So all we have to do is we have to try and find the surface load model that could explain the data. So Mike Davis and colleagues in their 2012 paper have shown a really nice correlation between the seasonal cycle in the crustal displacement, in particular the vertical component, which is the black line here, as a function of the day of year. And it can be correlated only when you combine the mass changes cycle happening in ice and air. So the individual components are shown here, but when we combine the air and ice mass, which is the solid blue line, then it corresponds really nicely with the seasonal cycle of seasonal oscillation of vertical displacement. So we also decided to use both the ice water mass transport, that happens on a horizontal direction, and also the vertical mass transport, which is essentially related to non-tidal atmospheric oceanic mass redistribution. And so the first step is that we choose our load model based on the GRACE data. So GSM and GSC, they respectively capture the ice and air mass, if you may. And here is our model prediction. In black, we show the observation, and in red are the GRACE-based model prediction. So we find a pretty good fit, I'd say, for the vertical component as expected. But for the horizontal components, the model prediction is really flat. So you cannot really capture those big jumps that we saw in year 2012 and also in 2010. And to simplify the interpretation, so I'm going to focus on the data in 2012. And so here is again this trajectory on map view. And so if you just look at the 4 summer months, so the resultant displacement vector is something like that, and which had the amplitude of 1.7 millimeter per year, so per month. And so for the following 4 months, the bedrock was moving, in the opposite direction, and the amplitude was, roughly 1/2 of, the summertime amplitude. And the model predictions is shown with green here, and it is virtually 0. So now the question is, why the GRACE data is so good to explaining the vertical component, but not the horizontal motion? So this can be answered by looking at what we call the sensitivity gradient maps. So these are a theoretical adjoints map that show how sensitive a particular component of displacement vector, in this case, the vertical component U1, is with respect to the change in ice thickness. And similar plot here, just but for the horizontal components, in this case, north-south component of horizontal displacement vector. So the numbers here are basically show how many micrometer of GNSS signal is expected if we put 1 meter thick ice load per square kilometer area. And it's negative values everywhere. That is reasonable, because if we add certain load here, then it's going to induce subsidence in this particular station. And but for the horizontal components, we see a clear dipole. So meaning if you put load here, it's going to pull the GNSS station towards that load, meaning towards north. But if we put load on the other side, it's going to pull the station in the opposite direction. So it means that opposite direction. So it means that in order for generating the significant amount of horizontal motion, it just requires that large mass anomaly should be present, and it should have really a symmetric spatial structure. So you cannot simply have the uniform mass distribution, no matter how much amplitude, how big amplitude it could have. If you don't capture, if it does not have this spatial symmetry, it is not going to induce the horizontal motion. And with the GRACE data, this is precisely what is happening. So this is, by the way, one GRACE mascon that I used in my analysis back in 2017. I think it's a 3 degree by 3 degree mascon. But anyway, so GRACE gives us one number per mascon per month. So meaning no matter what number we throw in here, the contribution to the horizontal motion due to the load present in 1/2 of the mascon is going to get canceled out by the contribution from the other half of the GRACE load model. So, and it is also important to realize that the ring station that we are looking at here is really located at the neck of Ring Glacier, which is one of the fast flowing outer glaciers in central West Greenland. And so now onwards, so we're gonna interpret. We're gonna assume that the required asymmetry in a spatial structure arises from the mass changes happening at Ring Glacier. Oops, sorry. So the next thing, what we did was for a relatively short time period, we can assume that surface mass balance can represent the total mass balance of glacier. So SMB model capture the climatological processes such as precipitation, runoff, and evapotranspiration. And here is a high resolution map, high resolution product of SMB, monthly data products again. And then we did a similar calculation. So by the way, you could see really, the SMB products resolving, the changes in mass along the glacier, not only in Ring Glacier, but in nearby glaciers as well. So, and here is our results. So again, the observation is shown with red, and the GRACE predictions shown with green, and the SMB model predictions are shown with blue. So it looks like it has captured some of the signals, but there is long way. I mean, it is far from being sufficient. And but for the 4 following months, starting October 2012 through January 2013, so SMB model cannot even predict anything about even a fraction of signal that was observed at GNSS station. So we know that mass balance is a combination of surface mass balance and what we call the dynamic or the discharge, if you may call ice discharge, or the dynamic ice thinning or thickening. And so by the process of elimination, so now we're going to seek at a coherent pattern in dynamic ice ocean mass, water mass transport through a glacier. So now the process is fairly straightforward. So here I show the sensitivity gradient maps, which is rotated, along the direction of the resultant bedrock motion during the 4 summer months. And then we can, then there's the white line shows the boundary of Ring Glacier. And because this is the summertime of the, the extreme melt season. And so we're going to assume that, all of the mass anomaly arises from the Greenland domain. And so one of the ways of explaining the data would be either there should be excessive amount of accumulation here, or there should be excessive amount of melting going on here. And this is summertime of 2012. So it is logical to assume that, it was excessive amount of melting that must have been contributing or must have been inducing this amount of horizontal motion. And then we can do a simple inversion, and you can even quantify the centroid of the mass anomaly. And so the uncertainty here really comes from the fact that we did a lot of experimentation with distributed versus concentrated load model. And yeah, so then we can also do a similar calculation for what happens, in the following 4 months, and we could calculate the accumulation of mass by about at a rate of 0.8 gigaton per month, and associated uncertainty is shown here. And you can play this game, from on a monthly basis. So basically going from June, July, August, September, it was like clockwise motion of the bedrock position, and the corresponding centroid of mass is really traveling down glacier. And same is true in this case. So remember that in this case, the mass anomaly is negative because it's ice thinning. That's why the GNSS station is pointing away from negative mass anomaly. But in this case, it is positive. That's why the GNSS station is really following the direction of positive mass anomaly. And then by simply tracking the centroid of the glacier, we can compute the average speed of this wave-looking phenomenon. And so we find that on average, it's really easily, like 10 to maybe even 20 times faster than the average speed of ice, which is typically 1 to 2 kilometers per year. So the same data, so but a better kind of visualization, especially in here. So I show the relative I show the bedrock station here, and the glacier is flowing downhill or this way. And so the positive mass anomaly, the bedrock is really pointing towards that, and the negative mass anomaly is pointing away from that. And this is a corresponding real data, and just try to give a sense of what must have been happening or what might have happened in 2012 melt season in Ring Glacier. Okay, so this is pretty much what I wanted to share, but let me take a moment to quickly summarize the second half of my talk. So we presented an ambiguous detection of what we call the kinematic waves of mass transport at Ring Glacier. And we quantified that the amount of mass involved was significant. So it was on the order of 6 to 7 gigaton, and that was the significant amount of mass that was dumped into the ocean during the 4 summer months in 2012. And the kinematic waves are expected to travel down glacier following the extreme climatological events, such as excessive surface melting, for example, the one that happened in 2012. And so in an ongoing warming climate, so we expect that such excessive climatological, the extreme climatological events or seasons might get more frequent, and it could be more extreme as well. And so that means that we are likely to see this short time scale pulses of kinematic waves traveling down glaciers in many more glaciers than just Ring Glacier. And all we have to do is we have to keep our eyes on those. And so one important thing here is that the method that we use to detect this kinematic wave is really novel, which is based on the bedrock GNSS based at-swing method, and that really utilizes measurements of the ice-earth interactions. So we envision that if we can deploy more than one station, ideally on either side of a glacier. For example, I could envision deploying a multiple GNSS stations on the bedrock, maybe a couple here and maybe a couple on the other side. So if we have this kind of configuration, so then we should be in a position to monitor or to quantify the continuous and near real-time monitoring of glacial mass transport. And given the high temporal nature of the data set, so we should be able to disentangle, what is the discharge of meltwater versus the discharge of solid ice. And this would be the first step, towards improving our understanding of complex ice-water interactions that happens in subglacial environment. And then we'll be in position to understand how they possibly impact the short-term and long-term dynamics of the ice sheet. And that has tremendous implication for, improved sea level projection. So I'm going to talk about these ideas in one of my talks in the upcoming AGU fall meeting. So if you are interested in knowing more about that or discussing about the topic, then please feel free to make sure you attend my talk, and we can get the conversations going. With that, I like to stop here, and I'd be happy to take any questions that you might have.
Great. Thank you so much, Surendra. I see lots of people clapping with their Zoom hands. So thank you so much for that very fascinating presentation. We are glad to entertain questions. I ask you either to raise your hand or to put your questions in the chat, or unmute yourself. I see Annie, do you have a question you want to start us off with?
Yes, please. Okay, I would like also to congratulate Surendra for this very informative and excellent talk. My question is, you showed the spectacular reduction of the misfit between measured and model uplift by taking into account the short-term viscous response. And my question is, I suppose that this short-term viscous response is not taken into account in the GIA model for Greenland applied to GRACE data. And what would be the effect on GRACE results if such short-term viscous response were taken into account?
Yeah, that's an excellent question. So actually, we just had a paper came out, detailing these ideas. And so we have a table in the supplementary material, which is really dedicated towards the impact of this short-term viscous response on the GRACE data. And if I recall, okay, so this is the GIA three-dimensional model, right? So it does not really account for the ongoing viscous response to post-lethal ices, the glaciers and sequence. And so even though it has a significant spatial structural variability, so if you really sum over the entire ice sheet, the impact of the GIA model, at least this particular model, on the GRACE data would be about -2 gigaton per year, something like that. So pretty much zero. But
Okay.
when you add the short-term viscous response, then it's gonna give you about 20 gigaton, maybe 25 gigaton per year. So that's the difference, on the order of 20 gigaton per year.
Okay. Okay. So thank you very much.
So thank
Great.
you.
All right, Jeff Freimuller has his hand up.
Yeah, thanks. Is my sound working?
Yes, we can hear you.
Great. Yeah, thanks again. I also would like to thank you for a really informative and interesting talk. I think it's really exciting that you found what looks to me like very strong evidence that we have to be considering post-Little Ice Age changes. I do wonder, though, if it has to be a time-dependent viscosity or if it really could be stratification. I ask that because I'm a little bit skeptical of the ability of the seismological models to really resolve those relatively shallow structures, and the kind of viscosity you're getting looks a lot like a regular asthenosphere, like what you would see in many other places. So yeah, I'm wondering if have you considered whether a stratified somewhat stratified model with a low viscosity asthenosphere layer would potentially fit the data worse or better or about the same as the kind of model that you've shown here?
Yeah, I mean, this is an excellent point, right? I mean, so one thing you could do is, I mean, we can take one of the two routes. So one would be, as you just said, we can further stratify the upper mantle and maybe invoke asthenosphere, as you said, and I mean, because it's an inverse problem. I mean, we can come up with whatever viscosity that is required for asthenosphere to minimize the data model speed. I don't see why you can't do that. But I think, there are a couple of reasons why we decided to kind of advocate for the time-dependent rheological model rather than the asthenospheric, rather than inducing or invoking asthenosphere there. So the first reason is that it's a recent paper, 2010, I'm sure you must be familiar with. This is by Toyokuni. But I know you told just before that, seismic data are not so reliable. But if we really look at here, they have this, P-wave velocity anomaly, as you can see, for different depths in the upper mantle viscosity, in the upper mantle. So the impact of the outstanding hot stream, which is clearly shown here, is really, it's really kind of local or regional, if you may. And so it persists, of course, in the upper 200 kilometer. That's maybe typical depth of asthenosphere, but it's not really propagating all the way to the rest of Greenland. So this is one reason why. And if you really think of the distribution of data, we cannot really compare this area, for example, versus rest of the Greenland. All we have to compare is the along the margin area, because that's where we have the data, right? And so we only have a handful of data in here, and that might, I mean, that is affected by outstanding hot plume. But this is one reason why we are kind of reluctant to invoke the asthenosphere. Again, to reiterate the same point, possibly the asthenospheric effect is somewhere here, or this outstanding hot plume effect, and we don't see anything else elsewhere. So this is one reason. And the second reason is that the EBM model is really something that is being developed by the experimental rock physicists, right? And they look at they do all kind of torsion experiment and so forth, especially Fowler and Jackson have been leading the effort. And what they have found after decades of lab experiments is that the nature of deformation of mantle is really a broad band, if you may, right? So it has a relaxation that happens across time scales. And so it's just really compatible. The EBM model is compatible with that, those kind of lab experiments in first place, in general. And also the seismologists are using the EBM model to better predict, I guess, to better model the post-seismic deformation. So, just to be in line with what other communities are doing, maybe, EBM would be a route to take, but, it's certainly not we don't have a definitive answer yet, whether, we should abandon the idea of invoking asthenosphere. But it would be good to, at least explore in the both direction and see,
Yeah, thanks a lot. I think either way, I think you've really shown that we need to consider we can't really consider it as a constant GIA plus an elastic problem. It really is more complicated than that. And I think regardless of what the exact mechanism, I think that's pretty clear in your results. Thank you.
Yeah, fully agreed. Thank you, Jeff.
Great. Crystal has her hand up.
Hi, Surendra. Thank you for the very interesting talk. I was wondering if you could comment maybe on how you go from the volume variations that you get from cryosat onto the loading model that you use, because this requires a model for the density of ice or snow, and they seem to be quite variable. And I was wondering how it could impact your results of residuals between GNSS and your loading elastic model.
Yeah, that's an excellent question, Crystal. And so honestly, so Johan Nilsson is the guy who helped me to process the cryosat data and apply the front air content correction. And Nicole Slagle is also involved in this project. So I guess basically they used, at least for this analysis, the RACMO-based estimate of front air content. I can come up with more informative, more details about how they actually apply the front air content. But yeah, I think that's all I can say for now.
But maybe do you know about the variability of those models and how it could affect your results, maybe?
Yeah, it's gonna. So we try to be a bit more generic in terms of the uncertainties associated with not only crash site data but also the other kind of data. And so this we believe that in our uncertainty estimate, which is pretty tall, I think. Yeah, here. We must have captured the potential variability or potential uncertainties associated with the front air content treatment and how we transfer the information of volume change to mass changes. But this is certainly one area we can further investigate to further improve or fine tune these results. Yeah.
All right, thank you.
But one thing I can tell, it can change the residual maybe by a millimeter here and there. But for me, the big picture thing here is that it's not going to resolve this data model misfit altogether. So it could be that instead of 6 millimeter here, it could be 5 millimeter. So that's a separate thing. But all in all, these residuals, they also right here, is reasonably robust, and it is not really dependent on how what methods we use to transfer the volume change information to mass change information. Thank you.
Thank you.
Great. All right. Well, our time is up for today. I want to thank Surendra again for a great talk, and hopefully it will be successfully recorded and it will be available. We will not have a webinar in December. We hope to see some of you virtually or in person at the AGU meeting, and then we will resume in January. So until then, hope you all have a good day.
Thank you, everyone.
Bye-bye. Bye-bye, everybody.